In the last video of Part C, I'd like to give you a comprehension question set. Yeah, so this is our first comprehension question set. In this one, I want to talk about 3 questions. Three, so not very hard, all related to polynomial evaluations. Horner's rule. Yeah. All right, so let me start the first question. Yeah. First, I like to, explain the notation for the question number. Yeah. Here you can see CQ1 means comprehension question set number 1. Yeah. After that, dash for the question number, I divided into 2 parts. Yeah. The first part, Q1 before the dot, that's the question number in the current set. Yeah. So I call it a local question number. Yeah. But after the dot, another number, I want to order all the comprehension questions for this class. So that is the global order number. Okay. So here 1.1, because we start our first comprehension question. Its local question number is 1, and a global question number also is 1. Yeah. All right. So let's look at a question. How many additions do we need when we evaluate the following polynomial? Here, I didn't give you the standard way to write the polynomial. So here, I give you the way, so you can see the subscripts, the exponent number for each term, they do not use the natural numbers, right, in order. Yeah, 1, 2, 3, 4 consecutive natural numbers, right? Yeah. Here, the subscripts, I choose jump, okay, not consecutive numbers. So that, that way can make the question a little harder. When you count the number of additions, you need to figure out what way do you use to get that, right? Yeah. So here, remember the question I designed here, I want to give you a chance to practice the counting technique we use in the notes. Yeah. Counting by reference. So that is the method I want to practice. The counting technique, the counting by reference technique. Yeah. What kind of reference you need to determine that? Yeah. But similar to the examples in our notes, the first plus sign we can associate with the first subscript 3. Second plus sign associate with second subscript 7, and so on. Okay? Yeah. Then the last plus sign associate with the last subscript. Yeah. Now, to count the number of additions, yeah. So when you count the number of additions equals, how do you count? The number of elements in the set 3, 7, 11, 399, right? Yeah. The number of elements in the set. So the next question is, how many numbers in the set? You count that. Yeah. So that's the reference technique. The reference is you replace the original mathematical objects, addition addition objects by another mathematical object, subscripts. Okay, yeah. So addition object replaced by subscript objects. Then you count the number of subscripts. You get the answer. Okay, all right, yeah. So to count that, we need to find the rule, right? Yeah, all right. 3 equals 4 minus 1, right? Yeah, 4 times 1 minus 1. How about that? Because we know the difference between two adjacent subscripts equals 4. The difference is 4. So that's why, we use a multiple of 4. Then we change the number. Yeah. Multiple of 4, you need to minus 1 to get 3. Yeah. 7 equals 4 times 2 minus 1, and so on. Okay? Yeah. All the way down. The last one, 399 equals 4 times 100 minus 1, right? Yeah. Now, when you count the number of subscripts, do you just count the numbers here from 1, 2, through 100, right? Because that way, much easier to count, right? So that answer is 100. How about that? So that answer is 100. Okay, yeah. So in this way, you can count number of additions easily because you choose the right reference. Okay, all right, yeah. Try to get the idea of this method, yeah. Because later I may change the format of subscripts or superscripts. Yeah, the rules I may change, but the basic idea is the same. Yeah, and you try it by yourself if you can solve it using this method. All right, so that's the first question. The second question, this one. Yeah. Given a polynomial as follows. Yeah. So I give you explicit coefficients for this polynomial. Yeah. To evaluate the minimum number of multiplications that one needs is, so these options. Okay, yeah. Here, to answer this question, so you need a background of our, Module 1, right? Yeah, part A, part B, yeah, but not part C. Part C, we talk about data structure. Yeah, so different topic. Yeah. Part A, part B, yeah. Polynomial evaluation, the Horner's rule. Yeah. So first, you need to connect to the Horner's rule, right? Yeah. Here, the coefficients given here, pretty random way. Yeah. The random way, the reason I say that, because you cannot find an explicit rule there, right? You cannot find some special rule here. So for that reason, you cannot take advantage of the special structure. In that situation, if there is no special rule pattern, or we call it pattern, if there is no special pattern in the given polynomial, then we just use the Horner's rule. Okay, yeah. So by Horner's rule, we know the number of multiplications determined by the highest degree term, or we call it leading term. Leading term. Okay, yeah. All right, yeah. Leading term, yeah. The leading term, its coefficient is not 1. If it's 1, we can save one multiplication, right? Yeah. The leading term, its leading coefficient is not 1. It's not a positive 1 or negative 1. Yeah. Other than positive or absolute value 1. Yeah. In that situation, the number of multiplication equals the degree number, the 5, by Horner's rule. The answer is 5 multiplications. Yeah. All right, so the minimum number of multiplication that one needs, option C, 5. Yeah. 3, 4, can you make it? Can you evaluate this polynomial by 3 or 4 multiplications? It's possible, the probability is extremely low. There is a very small possibility that one can do it, because I cannot say 100%. Nobody can do it, right? Yeah. But that possibility is extremely small, so we don't want to spend our time to explore that possibility. Okay? Yeah. We don't want to spend a lot of time to explore that possibility. We just apply the Horner's rule because it is a simple solution. So we take it. Yeah. If you take the Horner's rule, you get answer option C. Yeah. Now, if you option D, 6 or more, that's not the best solution. Yeah. Someone can do better easily with 5 multiplications. Yeah. So for that reason, your solution is not good. Okay? Yeah. All right, so that's the second question. Then the last question of this part. The third one, to evaluate a polynomial, the general polynomial form, for some positive integer n. The number of multiplications is always greater, the key part, always greater than the number of additions. This statement, true or false? Okay, yeah. So this is a simple question. If you have the right background, you can answer this question easily. Yeah. Here, the right background, so that is the topic we covered in part A and B, polynomial evaluation, Horner's rule, right? Still, so this is a Horner's rule question. Okay? Yeah. You just apply the Horner's rule, the number of additions, yeah, we know that's n, right? The number of multiplications also n, right? Equal, the same. So then always greater, that's not correct, right? That is not correct. Yeah. Okay? So you know the answer is B, false. But here, although this question is so simple, so easy, yeah, but you can imagine. So why I designed this simple question, yeah, the purpose is very simple. If one student does not know Horner's rule, right, you can think about, so what is the possible solution? If one student just skip the Horner's rule topic, okay, come to this question directly, you can imagine the answer is very likely true. Because by our general impression, yeah, definitely you need more multiplications than number of additions by an ordinary people's intuition, right? Yeah. So although it is a simple question, but it's a good question to be used to check if one person understands Horner's rule or not. Okay, so that's simple. Yeah. All right, so here I just want to stop here. Yeah, and next we will do the part D and complete module 1.